So hi everyone, and welcome to lecture 19 of ECE 3311 Principles of Communication Systems. And in today's lecture, it's going to be an exciting one because we have just moved from the analog waveforms to the digital ones. Okay, so this is excellent because what we've been looking at up until this time has been where we've had a message signal M of t. Well, okay, instead of hand waving, let me actually draw it. So what we've been having so far is we've had a message signal, right? M of t. And it was analog. Analog in the sense that we have information, okay, that flows as a continuum. So there are no discrete instances of data. You know, for instance, human speech, right? For instance, like, you know, the sounds that I make out of my mouth, right, is a sort of continuum, right? It's a continuum of amplitude values, continuum of amplitude values, and it's a continuum, okay, of time values, okay? So what ends up happening is I don't have no discrete amplitudes. Well, except that we did look at PAM and we did look at PCM, right? Where we did quantize the amplitude values to a select number of levels. So we did look at that, okay? But that was for the purposes of doing sampling that converted an analog waveform to the digital domain, but to do signal processing on it, represented as binary, and then convert it back into an analog waveform. But the information that was in that signal was not discrete, right? And then the other one, the continuum of time values, again, the information is continuous. It doesn't sort of like every time instant it has something that was unique and very specific. It's like every infinitesimal point in that curve has some sort of information that is important or is useful or is part of the message signal, right? Awesome. But now, okay, so this here, okay, so first of all here, this was for sampling. Okay, sampling purposes where we convert from analog to digital to analog again. Okay, we saw both of those. And the continuum of time values, like every t counts, right? Because it's unique. Okay, but now what we're going to be looking at, very, very super duper important. What we'll be looking at now, starting with lecture 19, okay, is we're looking at digital modulation. So what does that mean? So we still have an M of t, okay? But what happens is that M of t, what happens is the information is conveyed in discrete periods, okay? So we call these symbol periods. TS. They're uniform. And that within every symbol period, things like amplitude, okay, things like phase, things like frequency, all of these, okay, per symbol period dictate what type of information is being contained, and it's done so in terms of representing a very specific binary pattern, right? So what happens is, for instance, e.g., if I have the binary pattern 101101, this might represent a specific amplitude, a specific phase, and a specific frequency, right? I'm going to put I. And that 011011 represents another amplitude, another phase, another frequency, okay? And what happens is at every TS seconds, another set of binary values is produced, and another one, and another one, and another one, and another one, and another one. Okay? So this is critical. We didn't see this with M of T in terms of the analog waveforms, right? Human speech just flows. Every infinitesimal value of T. Here, every TS seconds, we have a specific amplitude, phase, and frequency. Every TS seconds, every TS seconds, every TS seconds, every TS seconds. And if in this case, there are 6 bits, right? So within that TS, there are going to be 6 bits, okay, that are represented in it. Okay, so there's the bit period. And symbol period. All right. So that's where we talk about like these digital modulation schemes. We have binary information. Binary information, the source of that binary information could come from any source, right? And then it's converted into an analog waveform that every TS seconds takes on a new amplitude, phase, and frequency representation. So that's what the next several lectures are going to be about. So we're instead of doing like M of T being a continuum of values, it's going to be very discrete set. Doop, 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 doop. All right. So let's go to it. Okay. So surprisingly, we still use the same formulation here, right? So what we use here, we still use that same exact mapping. Still kosher. This is still allowed. Right? So we still use the general expression for mapping between baseband and passband. Very, very important. So, and what is that again? S of T or V of T, whichever sort of notation I decide to use that day, is going to be equal to G of M of T, e to the J 2 pi F C of T. So now it's this mapping function here, right? So this mapping function is very important because what it's going to do is it's going to convert binary to some sort of amplitude value or phase value and or frequency value. And that's going to be some sort of complex baseband representation that then is upconverted to a carrier frequency FC. This is going to be excellent. Okie dokie. So we got that. So let's dig in. There's several types. So there is things like OOK. Okay, yeah. On-off keying. We're going to be looking at that today. On-off keying. Okay. We're going to be looking at something called BPSK. Binary shift keying. And then finally, differential shift keying. And this is just a start. There's actually a multitude of different types of modulation schemes out there. Just want to check. I'm worried my volume is it low? Surprise, it's actually not that bad. All right. So we take all of these guys. All right. So this is amplitude shift keying, otherwise known as on-off keying. And what it is unipolar binary signal, right? So what it is if it's binary 1, you get a pulse, and if it's a binary 0, you don't. It's there's no voltage level, right? So that's actually quite nice. So it's almost exactly the same sort of formulation as if you had like the passband. So let's actually look at this. Let's look at this. So what this is going to look like. So let's say we look at ASK. So ASK is another name for on-off keying. Well, on-off keying is the binary version, but ASK is a more generic version. So let's draw this. So first of all, there's this terminology called M-ary. So M refers to all the possible physical electromagnetic characteristics in terms of like the different levels of amplitude or phase or frequency. So it represents M possible combinations that uniquely describe the different binary patterns, okay, that can be used, that can be conveyed using that modulation scheme. So like, what do I mean? So let's say this is M-ary amplitude shift keying. So amplitude shift keying. Okay, so M-ary means M equals 2 to the B. B is the number of bits represented, okay, by a symbol. And the symbol we talked about already. It could be a unique, it has to be a unique amplitude and or phase and or frequency. Okay? So what does this mean? So the OOK is a form of 2 ASK or binary ASK. And what that means is, let's say a binary 1 is an amplitude value of A, and a binary 0 is an amplitude value of 0. Okay? So if I had something like this, and very importantly, every TS seconds, so I'm going to draw the little ticks here. Okay? If I had 1, 0, 1, 1, 0, 0, 1, 0, what it's going to look like is something like this. A, 0, A, 0, 0, A, 0. And that's it, right? So that, folks, okay? So this here is my M of T. That's my M of T. It's exactly the same as if you had an analog speech signal or anything of that nature, except that here it's defined by 0, TS, 2TS, 3TS, 4TS, 5TS, 6TS, 7TS. So what ends up happening is the only difference is there's a distinct change in its physical properties every TS seconds, bloop, 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 because it represents a binary pattern. In this case, it's binary. In this case, because there's only 2 values, it will only have a change, very distinct change between one physical parameter and another, in this case, amplitude. So now, how does this look like at passband? Well, in passband, It's going to look like this. So what's going to happen is this here, okay? Well, this thing is literally, let's say, AC m of t. I just put a constant there. You don't even need the constant. But now, every ts seconds, this either has an amplitude value of a or amplitude value of 0. Right? But it's all real. Okay, so we know this is real. Great. So if we apply all of this and we do Euler here, right? So this is going to be cosine 2 pi fc of t plus j sine 2 pi fc of t. What do we get? What we'll get is this is real. This is real. The imaginary will be removed by the real operator. I'm going to get AC m of t cosine 2 pi fc of t. Oh, that's just fantastic. What does this look like? This almost looks like AM, but here's the diff. Put the tick marks again. Very important because now the period, symbol period, is critical. Just FYI, when you only have two options, symbol period equals bit period. Okay? Because the number of bits represented per symbol is 1. Therefore, they both identically have the same amount of time. So now, if we go back, so it's 1 0 1 1 0 0 1 0. Yeah, okay. 1 0 1 1 0 0 1 0. Okay, so what we'll get is something that looks like this. And then you get cosine modulated inside of it. Beautiful, huh? Right? And then some more here. I'm not really counting the period, so the frequency is actually probably way, way, way off. But you get my point. Now, this is a passband representation of that on-off keying, right? That is digital modulation. Now, I did mention M-ary. So what happens if, let's say, M is equal to 4? That means 4 is equal to 2 to the B. B is equal to 2, which means I have 4 possible combinations, 4 possible representations, physical waveform representations, that uniquely represent 2 bits each. So let's say A and the binary pattern B1, B2. So let's say I have mirror. How about I have this? So I have 1, 2, 3, 4. And then I have the binary, I have a binary pattern 1, 1, 0, 0. 1, 0, 1, 0. So let's say I have something like that. Okay? Like, how does this work? Exactly the same way, friends. So what happens is this is going to look like this. And then let's say my symbol period looks like this. I'm making it a little bit smaller so I can actually have some really cool things to show. And suppose, binary-wise, because how many bits fit in one symbol? 2, right? That's the mapping. So let's say it's 1 0 1 1 1 0 0 0 0 1 1 0 1 0 1 1 0 0. So if I have something like that, what does it look like? So this guy, that's going to be a 2. Right? 1 1, it's going to be a 1. 1, 0, it's going to be a 2. 0, 0, it's going to be a 4. I'm very sloppy about that. 0, 1, 3. 1, 0, 2. 1, 0, 2. 1, 1, 1. 0, 0, 4. So now that I have this, let's get rid of that line because it looks confusing. Now that I got that, okay, so that's my amplitude value. So now what I do is do the same thing I did before. Create the envelope. So that's the top envelope, and then I do the bottom one. And now I fill with that cosine. Okay, and that is 4 ASK. So 4 amplitude values. And each represents 2 bits. Okay. So this is digital modulation. Wait, same sort of like structure as an analog modulation scheme, but very critically TS, symbol periods. And you can distinctively see that in your passband signal. All right. Okay, cool. So now, what's next? Can we vectorize this waveform? Yes, we can. So yes, we can. So here, like, let's say we look at M-area ASK, right? What we can do is to vectorize is when we vectorize, we're creating something called a signal constellation. And what that means is, just like, what this means is, what are the possible amplitude values? And it's like, okay, so amplitudes. And we had what? We had A, 2A, 3A, 4A. And this had what binary patterns associated with it? So it was 1, 1, 1, 0. 1, 1, 1, 0. 0, 1, 0, 0. So that's my signal constellation diagram. As we're going to see later on, this is going to be a very powerful tool, because what we'll use this for is things like, for instance, when we have 2-dimensional modulation schemes, and you can actually see the impact of things like noise, the uncertainty that's thrown in by the communication channel. All right. All right. So now, so the next guy, binary phase shift keying. This, folks, is actually quite powerful. So binary phase shift keying. So binary phase shift keying, same concept as ASK, right? Binary ASK, but instead of changing the amplitude, we change the phase, right? So the expression we have here, this is exactly exactly the going from the baseband to the from complex baseband to the passband. It's exactly that. Like, let's go to it. Okay, so we go here. So let's say we could choose one phase. Phase 1. And binary 2 can be phase, and then let's say binary 0 could be phase 2. And so what ends up happening is if we do this, again, our general representation correct? What we know okay? And so these T's, right? Like, so M of T can either produce one or the other every TS seconds, right? Same thing. It's all about the symbol period. And we know from Euler, this will be cosine plus J sine okay? Cosine gets removed by the real operator. And what we get at the end of the day is this. And remember, this can either be for binary 1, phi 1, binary 0, phi 2. Cool. Every TS seconds. Cool. Cool, 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 cool. So this is very powerful stuff, right? So what ends up happening is with this case, and we can also decompose it, right? Like we can totally decompose this. And what this will look like is the following. So first of all, as you saw, you could also use trig identities, and you can decompose this and this out. And in the notes, you also saw there was also a constant phase term. Sure, you could do that as well. But what you could do is if you use trig identity, okay, what you can get is this is cos A plus B, right? So if this is cos A plus B, this will be equal to cos A cos B minus sine A sine B. Let me write it out, right? Cos A cos B minus sine A sine B. Cool. So what does this look like? Oh, it's actually kind of cool stuff. So notice I have this and I have this. So I have a sine and I have a cosine that are multiplying against, sorry, here. So these high frequency components, sine and cosine, and they're multiplying against the cosine of these phases. All right. So what this will look like, okay, is suppose that I let phi 1, So let's say, as an example, 1 is mapped to phi 1, which is 0 radians. And 0 is mapped to phi 2, which is pi radians. So what happens? Well, first of all, sine, the second term, disappears. Okay, cool beans, right? And then what ends up happening is, what do we have left? Well, what happens is, if we do this, is we have, first of all, the FCT is a constant. So it's, but what will happen, okay, is what's cosine? What's cosine of 0? Well, it's going to be 1, right? So let's make also an assumption. So assume, okay, dp is equal to 1, okay? So what we get, every TS seconds, AC, okay, cosine 2 pi FC of t, and then cos of this, which is either going to be 0 radians or pi radians. What's cos of 0? 1. What's cos of pi? -1. Ah, ha, 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 ha. So this is actually really important. So every TS seconds, what happens? So let's say 0, 1, 1, 0, 1, 0, 1. So this is going to be super interesting. So we know that there's going to be a multiplication by cosine. So the first thing you want to do is this guy here. So I'm either going to get a 1 or a -1. This is going to yield a very, 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 very interesting waveform. So what we're going to get, let's say we just do this thing first. So what's 0? Well, 0 is going to be -1, right? What's 1? It's going to be +1. So that's 180 degrees phase shift. We're most definitely going to see that. Again, 1, -1, 1, -1, 1. Okay. Now let's put the envelope. What is it going to look like? Here's the cosine. This I have to be super careful about drawing. And boom, 180 degrees phase shift. Yeah, see, I'm being very careful. 3 peaks up, 3 peaks down. And then when you have this, let me highlight this. This is actually super duper important. Check this out. That's 180 degrees phase shift. It's like suddenly the cosine wave like goes in the exact opposite direction. That indicates that we're changing from a 1, from either a binary 1 to a binary 0. So here, that's another one. That's why I don't like drawing BPSK. It's just like a real pain in the butt. Whoop, 180 degrees phase shift. Whoop, 180 degrees phase shift. And again. Beautiful. So these 180 degrees phase shifts, okay? So you're going to have some sort of phase detector, okay? Okay, to detect those transitions. And whenever you see that, and as long as you know which one's which, you can say 1, 0, 1, 1, 0, 1, 0. And the other thing that's really useful about this, notice that it's constant amplitude. So if you have any amplitude distortion in your channel, it doesn't really matter because it's only the phase that truly matters. But you're going to have to make sure you have a really good detector at your receiver to detect all those phase transitions, right? All right. In a vector sense, How does this look like in terms of a constellation diagram? So I drew the generic, sorry, a very specific case of BPSK. But in reality, let's go back to this. What happens is I have a cosine part and I have a sine part. So what I end up getting, actually, if you look at this, is I'm going to actually have an in phase and I'm going to have a quadrature component to my BPSK. In phase and quadrature, right? So if I look at the derivation and I work this all out, right? What I'm going to get is, if I break this all up, I'm going to get the following. I'm going to have, so for BPSK, what I'm going to have is, let's say this is my binary 1, and that's my binary 0. And this is if I select, okay? If this is a 0 radians value for m of t, and this here is pi radians value for m of t, and you might say, but where's this thing? So this thing, remember I talked about theta naught, like some built-in constant phase shift? That's that. So what happens is BPSK, if I designed it this way, it's going to look like this. I could also, but nothing tells me, right? So this is my signal constellation for BPSK. All right. So very powerful stuff. So this tells me quite a few things. So what this tells me is that I have this modulation scheme is represented in 2 dimensions, I and Q. If we go back to ASK, it's just along I because it's real valued only. In the case of BPSK, there's a in phase and quadrature. There's a real and there's an imaginary component for representing a binary 1 and a binary 0. So this is really awesome. If we now continue on, like, so let's say we go to the phase lock loops. Phase lock loops. And that's actually, you'll see this in project 4. Imagine you don't have a lock. What happens? Well, what you'll get, this is my attempt at drawing it, is you'll get this. Because what ends up happening is that you're like, so first of all, remember, so the distance out here is like the amplitude, okay? Or the equivalent of that, right? So what happens is that theta naught, if we don't have a lock on that, it's just going to spiral out of control, right? And we'll be unable to determine where the signal constellation points are on this, right? So this is when we don't have a lock. Okay. All right. So let me see if there's a good question. Okay, so if we look at class test, so let's look at an example. So an example of BPSK. So this is from class test 5 from B term 2019. Okay, question 2. So the question is, you have a BPSK waveform. Oh, wow. Okay, we know what those look like, right? And it looks like this. AC cos omega C T plus dP m of t. Okay? And m of t is equal to plus or minus 1. And the question asks, what the heck should dp equal to maximize signal efficiency? All right. So that's the question. So, or the other way is like minimize error. So, and they say justify mathematically. All right. So first of all, what you would do with this question is first of all, decompose this form into the other format that we had before, right? Use the trig identity. So what you'll get is AC cos and then cos dp. And that actually doesn't matter because cos of minus dp or cos of dp will be either or, correct? Now, the other one, sine does matter. The sine does come out of the argument, right? So it's going to be AC sine omega ct, right? And here, this does, so sine, we're going to have to do dp m of t. So this does matter, 100%. So here what happens is we can either have sine of dp minus 1 and we'll have sine of dp 1, right? And that's going to be equal to either minus sine dp or plus sine dp. Okay, so what we want to do is we want to maximize signal efficiency. So max signal okay, so what does that mean? So what we want to do is we want to simplify things. So first of all, AC cos dp cos omega ct, okay? What we look at, first of all, what matters here? Well, the thing is, the only thing that can really vary anything is going to be that dp term here. So AC, we can't really do anything. And this thing is just like, you know, some sort of carrier. So what should this be? And the thing is, we want to minimize that pilot term, right? So first of all, that's going to be equal to 0. And the way, then if that's the case, dp will, to get that, is some sort of multiple of like 2 pi, right? And then here, like as we saw before, so what we want to do is, we saw with the sine and the cosine business, right? So if we go back here, this is alternating between minus sine and plus sine, right? So this here, we're going to have like either minus sine, plus sine, minus sine, plus sine, minus sine, plus sine. And then, of course, if we choose pi over 2, what that's going to be equal to is it's going to be sine of a sine of pi over 2 is going to be equal to 1, right? So really it's going to be plus or minus 1. So at the end of the day, to maximize that, what we need to do is we need to maximize the data term, okay, and minimize the pilot term. Huh? What do you mean by that? So what does that mean? So what happens is, we want to get rid of, we want to eliminate, right? We want to eliminate this form, right? Like again, let's go back to it because maybe it was not clear. So we have AC cos dp cos omega ct. And now what we have is we have plus or minus sine dp, right? And we have what is it? And really that plus or minus, where is that coming from? So in fact, where that's coming from, that's actually m of t, right? Because this is plus or minus 1, right? So it was in here, but we found that that plus or minus actually can come out because of how sine treats plus or minus values, right? And then otherwise, so this here, oh, I'm sorry. And then there's also omega ct. So this is a carrier. Okay, so what? That's my message. Very important. That's what I want to carry out, right? This here carries 0 information. Why? Well, do you see m of t reflected anywhere in here? Absolutely not. It was in here, but plus or minus 1 times whatever in the cosine doesn't propagate out. So effectively, this here is just taking up dead air, right? So what we want to do is, how do you eliminate that cosine term? So the way you do it is you choose a value of dp that knocks it out of the game. And that, folks, is why we choose pi over 2. So now if we choose pi over 2 here for that dp, that makes it 1. And we have this pesky carrier term. Okay, fine, whatever. But our message signal is still preserved. Okay, so that's what dp should be equal to. It should be equal to pi over 2. Alrighty. So last but not least, in terms of the differential PSK, what it does is it has memory. So differential, what it does is it is the same as BPSK, but it looks at what the past, the immediate, just the previous value, the binary value, and the current binary value. And what it does is it takes those two, and I forgot if it's exclusive or not, but what it does is if it's like 1 and 1, it's 0, and if it's 0, 1, or 1, 0, it's 1, and if it's 0, 0, then it's 0. So what it does is it takes past value, immediate past value, and current value to generate what actually gets encoded in a BPSK format. Awesome. All right. So what we just talked about today is actually really important, because what we have just done, folks, is the all-important start of digital modulation, which you're going to actually see. So I know in the course we started off in a very big way. We started off with things like, look at how awesome all this analog modulation is. But things like 5G, Wi-Fi, Bluetooth, and all that, it's all digital, right? For the most part, most of the waveforms you're going to be dealing with in this course, and pretty much for a lot of your careers, are going to be in the digital format. So it's good that you understand the analog. It's a lot more sort of tangible. You can understand sort of physical concepts of how to manipulate electromagnetic spectrum. But now we're entering the part where you'll be applying a lot of what you're learning to your careers in the future. So with that, that concludes lecture 19 of ECE 3311. Okay.